Hello and welcome to the talk on Impact of Non-Idealities on Computational Networks built from low energy barrier magnet-based stochastic neurons. We are from University of Virginia. State retention in a magnet, regular magnet, is given by this energy barrier U, which I've drawn in a cartoon. And depending upon how high the energy barrier is, you can get various lifetimes of how quickly a magnet demagnetizes from its own position. In a memory technology industry, the target is 40 to 60 kT magnet because that gives you 10 years of retention. But for this purpose, we are looking at low energy like 1 or 2 kT magnets where your switching time is 50 picosecond to maybe 1 nanosecond. And what happens is that if you put it in an MTJ-like configuration, as we show, if you bias the device at 0, you get all these flips going on as you show in the right side. And then you can bias it one end or the other, and you can get a distribution where your magnet basically wants to stay in one direction or the other direction. So the magnet naturally kind of keeps moving between the two states at low energy barrier. And you can reflect this in an electrical way using a magnetoresistance effect, the TMR effect. And this device has been demonstrated at quite a few places. 2 kT, 3 kT is hard to achieve, but 10 to 15 kT, yeah, 10 to 25 kT, yes. And how can we compute with this? So this is the interesting part. So you can build, for one example is that you can build a low barrier magnet based Ising model of interacting spins. So you have all these spins SISJ donated here, and given the interaction matrix, the J and the B, in the bias matrix, you can get a certain energy Hamiltonian, and if you minimize the Hamiltonian, the ground state, that kind of gives you the solution of this class of problem called quadratic binary optimization. And probabilistic computing, because you have these low barrier magnets which switch kind of back and forth so quickly, you can sample the whole solution space of this Ising model at a very high speed. So you can actually get a full solution distribution very quickly. So that's the promise of probabilistic computing. So one of the ways of using it is to make a stochastic neuron out of it, which is a neuron which has a certain characteristics as we will talk about in a second, and it also has a certain noise on top of it. So if you build an analog stochastic neuron, you have both input and output can be stabilized at analog values, and if you have binary stochastic neuron, they are stabilized at binary values. So one example is that if you have this transistor and this MTJ based pull up pull down, and you add a buffer, you can get this device. So I'm showing you certain characteristics, and this is the equation. The V out that is the equation. So the output voltage kind of has this this kind of a tan hyperbolic characteristics, but there is also a noise term in it. So now question is, how robust are computing results from such magnets? So you can have lots of non-idealities, and we study just one aspect of it in this work. So what we do is that what happens if you have these characteristics which are mismatched due to, say, transistor and MTJ are mismatched, the resistances are mismatched, or there's a lot of variability in the transistor. So you can have the shifts and scaling of the characteristic in over XY direction, like in the output and the input direction, and you can have scalings. And you have all the other ones. So we are going to look at the shift and the scaling. So the examples that we are going to use is, one thing is like this Ising model, 3 neuron based. It's also a stochastic Hopfield associative memory, and you can use it to get all kinds of interesting phenomena. For example, an Ising model, you can get the ferromagnet or a frustrated spin glass, or you can use a Boolean function like, say, AND, XOR, or more complex functions. And there's also another example that we will use is a Bayesian network, where you have these kind of neurons driving in sequence. There's no loop back, and you can look at the mutual information in this network. So what we're going to do is that we're gonna see what happens if you have characteristic shifts. So if you see the shift in the input voltage, you see the binary, the Bayesian network is actually pretty decent, but your stochastic, the Hopfield network is generally much worse off. And this happens in the rest of the things that we are seeing. X scaling in the characteristics, it's much more dramatic in the Y shift, which is the output characteristics. So this is an initial study that kind of demonstrates that small deviation from ideal characteristics due to component mismatch do not produce significant errors. However, some circuits are more resilient than the others, and probabilistic circuits are reasonably resilient and well suited to be made out of technology right now. So we'll do more further study of some non-idealities in future. Thank you, and I hope you reach out to me if you have any further questions.